How to interpret PV diagrams for engine thermal efficiency. Have you ever looked at a pressure-volume diagram and wondered what it all means for engine thermal efficiency? Understanding these diagrams can really help you grasp how engines work. Let's break it down step by step. A pressure-volume diagram is a visual representation that shows how the pressure and volume of the working fluid in an engine change during a thermodynamic cycle. The area enclosed within the cycle loop on this diagram represents the net work output of the engine during one complete cycle. This work is the useful mechanical energy produced by the engine. Now, thermal efficiency measures how well an engine converts heat energy from fuel into useful work. It is defined as the ratio of the net work output to the heat energy input. To estimate this efficiency using a pressure-volume diagram, you need to analyze the shape and area of the cycle compared to ideal cycles, such as the Carnot cycle, which represents the maximum possible efficiency between two temperature reservoirs. First, identify the cycle loop. The closed curve on the pressure-volume diagram represents the engine cycle, showing stages like compression, expansion, heat addition, and heat rejection. Next, calculate the net work. The area inside the loop corresponds to the net work done by the engine. Larger enclosed areas mean more work output, which is a good sign for efficiency. It's also important to understand the different types of processes represented in the loop. For example, isothermal processes show heat transfer with volume change at constant temperature. Adiabatic processes indicate volume and pressure changes without heat transfer. Isochoric processes show pressure changes at constant volume with heat transfer. Thermal efficiency is influenced by the temperature difference between the hot and cold reservoirs. Processes at higher temperatures contribute to heat input, while those at lower temperatures correspond to heat rejection. Comparing the engine cycle with ideal cycles like the Carnot cycle can provide context for efficiency. The Carnot cycle on a pressure-volume diagram serves as a benchmark. Real engine cycles typically have smaller enclosed areas and less ideal process paths, indicating lower efficiency. In practical terms, studying a pressure-volume diagram allows engineers to identify inefficiencies, such as excessive heat loss or friction. Adjustments like increasing the temperature of the hot reservoir or reducing pressure drops during expansion can lead to improved efficiency. Pressure-volume diagrams are widely used for analyzing steam turbines, internal combustion engines, and refrigeration cycles to optimize performance. By understanding the relationship between the area enclosed by the cycle, the nature of thermodynamic processes, and the temperature conditions of the heat reservoirs, you can gain a clearer picture of engine thermal efficiency.